In this video, we're going to have a look at EMF and how it varies with current, internal resistance, and just in terms of graphically itself. So I'm sure you've seen the quick fact that EMF can be split up into the terminal voltage and the lost volts. The terminal voltage is the voltage that reaches the rest of the circuit except the internal resistance, and the lost volts, the combination of current and internal resistance, is just the voltage that's wasted because current has to flow through the internal resistance to reach the rest of the circuit. If we subtract IR from both sides, we get V is equal to EMF minus IR or minus IR plus EMF. Now, why did I write it like this? It's because what we have here is a straight line equation, which we know is in the form y equals mx plus c. And we have voltage on the y-axis and we have current on the x-axis. Now, if we write out the rest of mx plus c and compare coefficients, what we see is that because the y-axis is covered by the voltage and the x-axis is covered by the current, if I get another highlighted tool out, that tells you that m, which gives the gradient of the curve, gives you the minus of the internal resistance. It also tells you that the y-intercept gives you the EMF. So here, the y-intercept of the graph, where it crosses the y-axis, will give you the EMF, and the gradient of this graph would give you minus the internal resistance. That's going to be very useful in part B, but before we do that, let's explain why terminal PD decreases as the current increases. Well, the EMF is the total voltage that's provided by a battery. That's going to be constant because a battery can only supply so much potential difference. That potential difference is splits up across these two types of voltages like we mentioned. If the current is higher, like it mentions in this part of the question, the internal resistance of course won't vary, but the lost volts would actually increase. We say IR increases. Now that's important because if the EMF is constant, but the lost volts increases, that means that the terminal PD has to decrease so that it can still add up to that same constant EMF. So that's what you'd say here, the terminal PD has to decrease because the lost volts increases and the EMF is constant. So the terminal PD, it must decrease so that the EMF can stay constant. Otherwise, if it doesn't decrease, then these would add up to a larger EMF, but we don't have a larger EMF. Again, it stays constant. So let's say terminal PD decreases so that the terminal PD plus the lost volts can stay constant. Perfect. Using the definition or information I introduced beforehand, we know the EMF is going to be the y-intercept. It's very hard for you guys to see, but that will be 1.52 volts in this case. The internal resistance, to find that, well, let's pick out two coordinates. We have 0, 1.52. We can also use the coordinate here, 2, 0.6. We can say that the gradient is the change in y, which would be negative, by the way. It'd be the 0.6 take away 1.52 divided by the change in x, which is 2 take away 0. That gradient would give you minus the internal resistance. I'm just going to quickly type that in my calculator. So we have 0.6 minus 1.52 all over 2 would equal minus 0.46. So minus R equals minus 0.46, meaning the internal resistance itself would actually just be 0.46 ohms. Moving on to part C of the question, it says, draw on the graph the same EMF, meaning the same y-intercept, but double the internal resistance. That means that the gradient, which represents the internal resistance, would be doubled. So it'd just be a steeper line where you sort of signify that it's double the gradient. Here, how I signify that it's double the gradient is I halved this so that it appears twice as fast. The same EMF, but negligible internal resistance. Again, the same EMF means it starts at the same point on the y-axis, and negligible internal resistance means that there's no internal resistance. So it'd just be a horizontal line. And that's it. That's everything for this question. Be sure to leave a like if this video helped and subscribe. I'd appreciate it a lot. Thanks for watching, and yeah, have a nice rest of your day.